Okay, let's take a look at the first class of logic families, which is CMOS. So as we talked about earlier, there's kind of, with logic families are broken into two primary categories, TTL and CMOS. CMOS is the most dominantly used logic family today, and we'll kind of see why that is. So CMOS stands for complementary metal oxide semiconductor, and that's an acronym. So CMOS, complementary metal oxide semiconductor. And the metal oxide semiconductor, we'll see where that terms come from. CMOS is an approach that uses two transistors that act as complementary switches. Okay, so that's what the whole idea of CMOS is. So to understand kind of how it operates, it's good to take a look at the actual implementation of the transistors. Now we don't want to get too detailed into the device physics of how it works, but it is good just to kind of see the transistor implementation, just so at a minimum we know where the terminology comes from, and then it kind of sets the stage for why CMOS has some attractive properties, and also kind of where some of the feature size naming conventions come from. So within CMOS, you're going to have two types of transistors. One of them is going to be called an NMOS, and the other is going to be called a PMOS. And NMOS stands for N-type metal oxide semiconductor transistor, and PMOS stands for P-type metal oxide semiconductor. And so we've dived down a little bit further into what CMOS is. It's broken into NMOS and PMOS. We still don't know what the actual transistor looks like, but we do know that there's two transistors. One is NMOS, one is PMOS. So let's take a look at NMOS and see how we actually create one of these and where these terms come from. So NMOS, a transistor looks like this. I'm going to draw the cross section of one. So what we're going to do is we're going to take a piece of semiconductor material, and the most dominant semiconductor material in use today is silicon, but we're going to call this a semiconductor. And it's not just a semiconductor. So if you think about silicon, a semiconductor by definition is a material that is an insulator at absolute zero temperature, and then as the temperature increases it becomes more and more conductive. So we're interested in semiconductors that tend to make that transition in temperatures where humans typically live, where humans live. So if we have a material that is kind of on the cusp of becoming an insulator or transitioning from an insulator to a conductor, one of the things we can do is we can modify that material to either make it a conductor or make it an insulator very easily. So that's what makes silicon so attractive. Other than silicon is very abundant, it makes up a significant amount of the Earth's crust. So silicon it's a great material that's abundant, and it has all these properties in terms of temperature that make it very attractive to make electronics out of. So silicon by itself has a valence of 4, and that allows it to bond very easily with neighboring silicon atoms. So if you think about just drawing like a lattice structure of silicon, you're going to have all these valence bonds of silicon, and you can actually create these perfect crystals of silicon, and there's procedures to do this. There's companies that do this type of thing. They start with a pure crystal seed, and what they do is then they put it into a molten vat of other, kind of impure silicon, and then what they do is they slowly extract the seed crystal, and they allow the other silicon atoms to bond to it, and they form this perfect crystal. And so this is great. And one of the things you can do then is this doesn't have what we call a majority charge carrier. So you can think about it in terms of it's very neutral. So there's an equal number of electrons, equal number of positive charges, and so when you try to conduct current through this, it's a very poor conductor of current because there's not an abundance of electrons or a lack of electrons that would accept electrons. So one of the things you can do is you can come along and you can do what we call doping the silicon itself, And doping means inserting an impurity into this in order to modify its electrical characteristics. So let's say, for example, that we came in here and we have a valence of 4 on all the silicons, and we went in and we doped this and replaced one of these silicon atoms with something that had a valence of 5. So let's put something in here. An example of this would be like arsenic or phosphorus. And so if you have a valence of 5, one of the things that will happen is that it'll make the 4 valence bonds, but then what will happen is that you'll have actually an additional electron floating around that's looking to bond. So if you do that, and you do that enough, what will happen is that you'll have all these little electrons floating around here. You'll actually take the material and you'll turn it into something that has a majority charge carrier, which is an electron. So we have this majority charge carrier, which is an electron, or said another way, negative. So this then becomes what we call an N-type material. So an N-type material is something that has a majority charge carrier of negative charge. If we also said, okay, well, if you have a majority charge carrier, you also have a minority charge carrier of a positive. So it's the opposite of it. So this is a positive. Now, when we talk about positive charge carriers, we're not talking about using the protons within the nucleus. What we're talking about is the absence of an electron. So if you think about, an atom, you have kind of your protons and your neutrons that are sitting there in the nucleus, and then you have the electrons that are orbiting. And what we're talking about is that without destroying the nucleus, if you had something that had, let's say, a valence of 2 and you removed one of these electrons, then this atom wants to fill that orbital to reach a stable state by pulling in an electron. So what happens is that if you have an attractive force that pulls an electron into you, you look like a positive charge. So what we can do is the absence of an electron in a valence bond actually looks like a positive charge, and you can use that to make current, because if you think about a bunch of, let's say we have a bunch of nucleuses or a bunch of atoms that have what we call a hole, and I'll draw it as just a circle right here, and you have an electron here and an electron here. This hole wants to pull this electron over because it has a positive charge, because it has an equal and opposite force that's pulling this electron. And so since the electron has a negative charge by just nature, if you pull it over here, the force that pulls it over is equal and opposite. So an electron has a charge of 1.6 times 10 to the negative 19th coulombs. Well, so if you're pulling that over, so this is the charge of an electron, if you pull that over here, you could say that the charge, the effective charge of this hole, is going to be equal to positive 1.6 times 10 to the negative 19 coulombs. So if this electron then moved over to here, it would create a hole that would then pull this electron over, and then if that one moved over, then it would create a hole and another electron would be pulled in, and so on and so forth. So an absence of an electron can actually use to be conduct current. And the current is still electrons flowing. I mean, that's the definition of current. It's just a little bit different methodology, or a different way to think about the way the charge moves. So if you have an N-type material, you have a majority of electrons, or a majority of negative charge, which are used to transmit, or that makes up the current. So N-type material is where NMOS comes from. So the N in NMOS means that the current that's going to flow is done so using an N-type material. If I look at what a P-type material would look like, let's go over here and I'll draw the same structure, and you have some semiconductor, and we're not done with this semiconductor, talking about this semiconductor yet, but I want to show you where the P-type comes from. We could take that same silicon lattice that we had, which is very neutral because it's all the valences of 4 are bonded, so everybody's happy. And if we came along and now doped it with something that had, let's say, a valence of 3, what would happen there? So let's say that we want to dope this with a valence of 3, and an example of that would be boron. what we could do is, let's see what happens if we replace this with something that has a valence 3. Well, what's going to happen is it's going to make these covalent bonds right here, and one of them, though, will be not made. So what will happen is that this right here is an unbonded shell, or an unbonded location, and it is attracting, it wants an electron to be pulled into it. So what we've effectively done is we've created a positive charge there. So if you think about what we've done, we replaced one of these silicon atoms with boron, and we don't do it to the, we don't do it like every other silicon atom. We do just a small percentage of it, but it's enough to take this neutral material and have it have a majority of positive charge carriers. So now current can now flow by attracting electrons into this hole, and whenever an electron is pulled into here, what will happen is that it creates a hole, and so the absence of an electron is actually a method for current to flow. So this now is what we call a p-type material. And the reason is because it's got a majority charge carrier of positive charge, and it's positive charge, like we said, just to illustrate this, because it's kind of an important concept. It's not necessary. It's positive charge because it's missing an electron, so it's pulling an electron toward it. So what we call it is it's a hole. It's a hole that can be filled by an electron. So its majority charge carrier is a positive, and its minority charge carrier is equal to a negative. Now you say, what is a majority charge carrier versus a minority charge carrier? Well, in an n-type material, electrons, there's an abundance of electrons beyond the base lattice, and what that gives us the ability to do is easily move the electrons back and forth. That's not to say that you couldn't use positive charge to create the current, because if you put enough energy into the material, you could absolutely break one of these covalent bonds, and you could absolutely create what we call a hole in there if you put enough energy into it. So you can use you can influence the majority charge carriers, and you can also influence the minority charge carriers. And this is the key concept behind why it's so important to use these p-type materials and n-type materials, because we can influence the charge in there, and we can create junctions which allow us to control the flow of current. So we've kind of got this, just to summarize what we've talked about. You have two types of transistors, NMOS and PMOS. We don't know what MOS stands for yet, but now we know what N and P are. So N stands for n-type material, and that's how the current flows. P-type is the way that this transistor is going to cause current to flow using a p-type material. The way that n-type material is created is by taking a semiconductor and doping it with some other material, some impurity, in order to create an abundance or a majority of negative charge carriers. So N is where the N comes from. And then over here we have p-type material. We took the same silicon, we took the same semiconductor, and we doped it with an impurity in order to create a majority of positive charge carriers. Okay, so we have a majority. We also have a minority and minority, which becomes important later. Okay, so now let's look at what is the structure of this transistor. So here's what we're going to have. We're going to create two junctions in here. Okay, first of all, let's just draw the symbol for a transistor, just the general symbol or theory of operation of a transistor. So this is what the symbol for an NMOS transistor looks like, and we'll label these nodes here in a second. But it's essentially a three-terminal device, three functional terminals, and the way it works is you're going to have current that flows, and it's going to flow from this terminal right here to this terminal right here, and you're going to control the flow of current using this terminal. So you're going to use an electric field to either allow more current to flow or less current to flow. And what we want to do is we actually want to create a device which we can turn the current completely off, or we can turn it completely on. So let's assign some terminal names to this. Just for the NMOS, this is going to be called the gate right here, and this is going to be called the source, and this is going to be called the, this is going to be called the drain, and this is going to be called the source. Okay, and current flows from the drain to the source, and the amount of current that's going to flow is going to be dictated by the gate. Okay, now we're not going to go into the the details of the electronics of this. We just want a general overview of what's going to happen in terms of how this operates. And it's always better to kind of start with the NMOS transistor, and then when you go to the PMOS transistor, it'll make a lot more sense. Okay, so we have the symbol for the transistor. We kind of know the theory of operation, what we're trying to do. So let's draw in the structure. So I'm going to come along and I am going to create two regions right here, and I'm going to make them an N-type material. Okay, and I'm going to put that N-type material, these two little junctions, inside of a block or a body or the bulk right here. This is the semiconductor material that is going to be a P-type material. So I would take a piece of silicon and I would dope it with something with a valence of 5, and I would create a majority charge carrier of positive charge and a minority of negative charge. And then what I'm going to do is I'm going to create two junctions right here of N-type material. And I do it the same way. I go into this region and I implant impurities to make this an N-type material and an N-type material. These are going to serve as my drain and my source. So I'm going to have the drain and I'm going to have the source right here. And what I want to do is I want to figure out a way that I can make current flow between these based upon some control. Okay, now immediately you say, well, wait a minute, is current going to flow right now? I mean, I have some semiconductor material, they're still semiconductors, but it turns out that current won't flow because when you have a P-type and an N-type material that form a junction, what happens is current won't flow. So if I have a P-type and an N-type, what happens is it will form this depletion region just due to the way that the positive charges, that like charges repel and opposite charges attract. What will happen is that the electrons will move a certain way and the positive charges will move a certain way. And what you'll end up happening is you'll have a region right here which is depleted of charge carriers, and current won't flow. So if you just put this junction together, what will happen is due to the properties of the material, what will happen is that you won't have current flow through this. So it becomes a nice thing. So when you think about this right here, it'll actually form this little depletion region around here and current won't flow. And that just has to do with the properties of how this junction works. And if you think about what's actually happening here and why there's a junction, if you zoom in on this, you're basically going to have, if we look at kind of the charge carrier here, plus, 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 and we have minus, 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 and then we connect the materials together. Okay, so that's the junction right there. That is, the term junction refers to where the materials come together. Well, what's going to happen is that opposite charges are attracted to each other. So you're going to have the negative charges, and these are electrons, and over here the positive is an absence of electrons. The negatives are going to move over here, so you're going to have negatives here, and just due to the attractive force between these two charges. And then you're going to have positive charges which are going to move over here. So what's going to end up happening is you have positive charges moving this way and negative charges moving this way. And then you say, well, that just seems like it'll continue happening forever, because why won't they just go into equilibrium? Well, what ends up happening is that the negative charges come over here and they're still being attracted this way, but now these positive charges have been moved over to the right, and so there's now an attractive force back over here. So the electrons jump over here, but since the positive charges jumped over here, you start reaching this equilibrium where the electrons over here, the negative charges, are being attracted both to the left and to the right. And the same thing with the positive charges. They're being attracted to the right and to the left. So you end up with this region right here where this right here is going to form an equilibrium, and current will not flow through that. So this is the theory of a p-n junction, kind of using cartoon descriptions of how it works. But the key is that when these materials come together, they will inherently not conduct current. And that is exactly what we want when we build this semiconductor transistor, this semiconductor-based transistor. So I come along here and I now have my drain and my source, and I want to control how they work, or when they conduct current between them. So I have this whole concept right here where I have the drain and the source. I want to try to get current to flow through them. And when I do that, it's not going to conduct right here, but if I could turn this material right in between them from a P-type into an N-type, then a current would flow. So I need some way to basically alter the material properties of the semiconductor that exist between these two N-type channels. So what I'm going to do, and I can do that, it just takes energy. The energy that I'm going to use is, since this is electronics, I'm going to use an electric field. So I'm going to insert an electric field on here. And I want to do that, I want to do the electric field, but I don't want to directly inject current into here. I just want to influence the material right here. So what I'm going to do is I'm going to put an insulator right here. So I'm going to put an insulator, and then I need some way to contact an electric field, an external electric field. So what I do here is I'm going to put some conductor right here. And then I'm going to attach my control terminal, which is my gate. So I have this conductor, I have an insulator, and then I have a semiconductor. Now, here's where the MOS comes from. You have a conductor, that's a metal. The insulator it's actually formed with, let's see, where should I write it? The insulator is actually formed by an oxide. So it's formed easily with silicon oxide. So this SiO2 is the material that's typically used in these semiconductor transistor, or in CMOS, in order to form that insulating material. So it's just kind of taken on the name that the insulator is actually an oxide. Okay, so that's where the O comes from. So this is the O, and then you have semiconductor right here. So MOS is the structure of the control gate. So it's a metal oxide semiconductor, and that's how you control whether current flows between the drain and the source. So that finally gets us to where the MOS came from in CMOS, where it comes from in NMOS, and where it comes from in PMOS. We also now have this notion of, when I build an NMOS transistor, the drain and the source are going to conduct current using N-type charge carriers, or negative. In a similar fashion, if I went over and drew the PMOS, I'm going to create a P terminal here, a P terminal here, and a P terminal here, and let's just call it, I'll go the source here, and I'll go the drain here, and I want to make current flow between the source and the drain, or the drain to the source. Well, if I put in P-type terminals right there, I got to make sure that it doesn't just automatically, conduct current. So I had to have put that into an N-type substrate. So they're exactly complementary to each other. An NMOS transistor uses a P-type substrate. A PMOS transistor uses an N-type substrate. Why did I use the N-type? It's because a PMOS transistor is going to conduct current using P-type charge carriers, or positive charge carriers. So in order to alleviate this whole notion of current just flowing immediately, I had to put an N-type in there, and that allowed this junction to form, which inherently won't conduct current. Okay? Now the great thing about this junction, there's two great things about it. Number one is that it's not going to conduct current, but the second thing about it is that it is easy to overcome. Okay. Just like in the NMOS, I need to put a control terminal on here, and I'm going to put a metal and an oxide. Remember, the metal is, basically anytime you connect anything to something, you need a metal, and so you have, or a conductor. So I'm going to have this gate that's going to create charge right here, or going to create an electric field, and then I need an insulator because I don't want to just inject current into the material. I just want to influence the material. So now I have my two structures, and let's think about what I'm trying to do in an NMOS. On an NMOS, I'm trying to put a voltage here which will create or turn the material between these two terminals from a P-type to an N-type. So I need a P to an N over here. I need a P to an N, and then current will conduct. Over here I need to take an electric field and put it over here, and I need to take this N-type material and convert it into a P. So that's where I'm at right now. I have all the terminologies set up, and now it's time to finally look at how do I do this. Okay, so I come along and I'm going to put a small amount of positive electric field on here. So that was kind of a lot of electric field there. So I'm going to put some positive charge on the gate. What happens? Well, if you think about it, the metal itself is just metal. So it's just the entire thing immediately becomes positive. And then what happens though in the insulator is that it does this thing called polarizing. So it's not going to conduct DC current, but it will create these bipolar or these polarized little regions in here. So the insulator will actually go like this. Its negative charge will be attracted to the junction with the metal, and its positive charge will be repelled. So it'll create these little dipoles in here, and the whole insulating material would do that. Okay? So what that does is that it influences what happens at this junction right here. So now if you think about it, I've got plus charge or positive charge down here at the junction to the semiconductor. What does that do? Well, this material inherently was positively charged. So if you put a positive charge right there, it's going to push those positive charges away from this junction. And so I push all those away, and what's nice about that is when I push those positive charges away, I kind of form a region which is depleted of charge. Well, then what I can do is if I continue to add positive charge onto there, what'll happen even more is that I can attract the minority charge carriers. So remember, these minority charge carriers still exist in here. And if I make this field big enough, I can actually pull these things up into this little region right here. And what I do is I form a channel of electrons right at this junction right here, and that then allows me to conduct current. So this right here now is my channel, and as long as I put a positive enough field on the gate, I can actually alter the electrical properties of the semiconductor between the drain and the source, and once I form that channel, current will flow. Okay? Now current doesn't flow unless there's a voltage, so all I've done is I've allowed the current to flow. So then if I came along and I put a voltage between the drain and the source, current would absolutely flow. So I've done it. Now I have the theory of operation of an NMOS transistor. Let's take a look at the theory of operation of a PMOS transistor. I'm going to do the exact opposite thing. I'm going to come over here, and I need to push the N-type charge carriers. So remember, this is all N-type, this is all negative charge, and I need to push these negative charges out of here. So what I'm going to do is I'm going to put negative and a negative electric field here, or negative charge, and what that's going to do is the metal will become all negative. It'll polarize the oxide. So I'm going to pull the positive toward the top and the negative toward the bottom. Okay? So you can kind of see how I'm able to apply a negative charge to the gate, and I'm able to get a negative charge to this junction. And the reason I was able to do that is because there's an oxide between it, and that's the way that an oxide works is perfect for this application. So now I have a negative charge right at this junction. It pushes these negative charges away because like charges repel. But guess what happens if I keep continuing to increase that? It is going to attract the minority charge carriers up to this junction, and I will then form a channel of positive charge. As soon as that channel is formed, I have essentially connected the drain and the source, and now I will have current that can flow. Since this transistor acts in an absolutely complementary way to an NMOS, I can now draw the symbol for a PMOS transistor, and it'll make a little bit more sense. It's still got the 3 terminals, and it still has a gate, but I put an inversion bowl on the gate to show that it operates in the exact opposite way as an NMOS. And then when I label my terminals, I do it opposite. So I have a source on top, and I have a drain on bottom, and then the current flows from the source to the drain. So when I draw them like this, I still have the current that flows here and the current that flows there. Okay, so the final thing that we'll look at before we look at the actual gate implementation itself is this concept of a threshold voltage. So we talked about we needed to put a charge on here. We needed to put a certain amount of electric field, a certain amount of energy in order to bring this channel together. Well, we needed to have a certain threshold where we put enough energy there and finally the channel was formed. It turns out that it's defined as VT, and that's the threshold voltage. And the way it works is you need to have VGS greater than V threshold in order for this device to be considered on. So this is the condition that is on. And then over here, the way it works is you actually have plus and minus VT, so everything's kind of opposite. But over here what you have is you need VGS less than or equal to VT for this to be on. Okay, and so we'll kind of look at how that matters once we start executing things. Now we're going to use these as switches, but this is kind of the cartoon device physics of how these transistors work. So just to do a 10-second review, what we're talking about is CMOS. It is an approach to creating digital logic gates. It is complementary metal oxide semiconductor. C stands for you have two complementary transistors, NMOS and PMOS. Metal oxide semiconductor, or MOS, stands for the structure that you use to create the control of the actual transistor itself. NMOS transistors use negative charge carriers to conduct current between the drain and the source. PMOSs use positive charge, or holes, so positive charge, to conduct current between the source and the drain, and they're controlled by the gate. Okay? All right.